Welcome back, Honors Algebra 2 students. Algebra 2 students, this is section 10.6 on page 308 of your student journals. We are doing the last section of our probability unit. So in this section, there's actually a couple things that are going on in here, one of which we're actually going to omit or skip, and that's that binomial expansion. If you remember Pascal's triangle and where we did stuff where, let me see if I can find an example. Well, here, I'll just make one up. Remember when we did Pascal's triangle and we expanded something like a binomial to, let's say, the fourth power? We followed the rules on Pascal's triangle where, like, if you did, remember, like, kind of creating this formula or this this triangle, and then we used those as the coefficients of the first of all the terms, and then basically you started with like your first term raised to the highest power, the last term raised to the lowest power, and then you kind of went down. Well, anyway, so we already did that, all right? So what we're going to do is we're going to kind of use that knowledge and expand it to something with probability. And so what we're going to get into, and I'm actually going to move to page, we're going to do a whole lot in here. We're just actually going to look at one equation, which is a little bit weird. We're going to look at binomial experiments. So this is really the only thing in this section that I want us to kind of focus on. And binomial experiments are a very specific type of experiment and a very specific type of probability. So it says a binomial experiment meets the following conditions. There are n independent trials. In other words, like you might say something like, okay, we did something where, you know, you might spin something, 20 times. That's n, represents the number of times you did that particular experiment. So remember, an experiment is different than theoretical, right? A theoretical is like the mathematical or the odds of something happening, whereas an experiment is based off of your data. Each trial has only two possible outcomes, success or failure. So what we're looking at here is we're measuring the probability of success or the probability of failure, one or the other. And then the last condition, I guess, is the probability of success is the same for each trial. This probability is denoted by P, which kind of makes sense, and then the probability of failure is 1 minus P. So what this is saying, if probability of success is 40%, right? Like if you have a 40% chance you're gonna, I don't know, win the raffle at school, then that means there's 1 minus 40%, or in other words, 100 minus 40%, which is a 60% chance that you're gonna lose. So that's all that's really saying. So when you see this formula, we're gonna be using P and 1 minus P. So P represents the probability of success, and 1 minus P is the probability of failure. And that's what that kind of represents. Here is the that we're going to use. So for this binomial experiment, and it's the probability of success. So K successes. So K stands for the number of trials you're using. K stands for the number of times that you're doing. Like, so let's say, for example, you're doing 20 trials, right? You would represent K equals 0, K equals 1, K equals 2, K equals 3, all the way up to 20, because you're going to look at the probability of each individual trial and what the probability of getting that outcome is, for that particular experiment. And so the formula is NCK, so it's a combination. Let me zoom in here a little bit. So it's NCK. So the N stands for the number of trials. So let's, again, in our scenario, let's say we represent, 8 trials or whatever. K is what we talked about, like if we're on trial 0 or on trial 1 or on trial 5, that would be what we're putting here. P is the probability of success raised to the K value. Again, still K represents the trial we're on. 1 minus P represents the probability of failure raised to the N minus K. So this formula is really kind of a little bit elaborate. And so what we're doing here is we're using data to then create a histogram. You might remember histograms from middle school. And then what that does is shows us a distribution of all of the possible outcomes. And so what then we can determine is, which outcome is most likely. We can determine how the data is skewed, whether it's left, right, or normal distribution, and that kind of thing. So what I'm going to do is I'm going to jump ahead to our extra practice. Actually, I lied. I'm going to go ahead and grab your formula sheet first, because I want you to add this to your formula page. And so what I want you to add here is just that so this is for a binomial experiment. So I'm going to add this at the end here. So for a binomial experiment, our formula is, so the probability of k successes. What you're saying here is, like, if we did, like I said, if we did a trial out of 20, k successes means what's the probability of getting nothing correct? Like k equals 0. What if the probability of getting 1? K equals 1. What's the probability of getting 2? K equals 2. So what you're looking at is each individual kind of like time, I guess. So the probability of k successes equals a combination. So n, c, k. And then this is like times the probability raised to the k power times the probability, or the probability of success, or I'm sorry, the probability of failure, which is 1 minus p, raised to the n minus k. We're going to be using our calculators for this. I'm not going to have us do this out by hand in terms of like the math involved here. We're going to use the combination formula in our calculator just because it'll be easier. And I'm going to show you how to kind of more simplistically create this in your calculator so that you can go ahead and find the data that you're looking for. So let me show you an example of what we're going to be doing. So I'm on the extra notes, right? So on the 10.6 section. So we're going to do a couple examples together. All right, so the spinner is divided into 3 equal parts. Let x be a random variable that represents the sum when the spinner is spun twice. So again, right? Make a table and draw a histogram showing the probability distribution for x. All right. So what this means when we talk about the probability distribution for x, we're looking for, so this is kind of like a preliminary kind of table, I guess, if you will. So I make a table that's kind of based off of, 3 rows. So we have x, which represents the sum of the 2 numbers, because it says that we're spinning the spinner twice, and we're going to add them together. So x is going to represent the sum of our numbers. And then we're going to look at the outcome. Like, in other words, did I spin a 1? Did I get 2, 3? What did I get as when I spun the spinner? And then what's the probability of x happening? So when it asks you to make a probability distribution, this is really what we're looking at. All right, so the sum, if I spin any 2 numbers, I could get, 0, 0, 0, 1, 0, 2. I could get, 1, 1, 1, 1, 2, 1, 0. I could get 2, 1, 2, 2, 2, 0. So basically when I'm looking at my sums, I can get a sum of 0. I could get a sum of 1. I could get a sum of 2. I could get a sum of 3. And I could get a sum of 4. So those are all the possible sums that I could get if I spin the spinner twice. All right, my outcome would be the probability of getting, so if I get a sum of 1. So if I get, if I spin this, if the sum is 0, how many different ways in which I spin the spinner twice can I get a sum of 0? Well, there's only one way that I can get of 0, right? If I spin a 0 once and I spin a 0 twice. So there's one outcome that provides me with a sum of 0. So the probability of that happening, so now we have to think about the probability. So if we spin a spinner, so on the first spin, there's a 1 out of 3 chance, right? And then on the second spin, there's a 1 out of 3 chance of getting each number, which means the probability of each thing happening is 1/9, which means that 9 is the total number of outcomes in our scenario, right? There's 3 outcomes for the first one, 3 outcomes for the second spin, which gives us 9 outcomes total. So the probability would be the number of favorable outcomes over the total outcomes. So in our scenario here, there's 1 favorable outcome and 9 total outcomes. All right, let's look at 1. How many different ways can we get a sum of 1? Well, if I did 1, 0, or if I did 0, 1, I could get, I guess, 2 different ways in which I could get a sum of 1. Okay, so that probability is 2 out of 9. Probability of getting a sum of 2. So I could get 1, 1, I could get 2, 0, or 0, 2. And so that would give me 3 choices. That would give me 3/9, or I'm just going to reduce to 1/3. Probability of 3, I could get a 1 then a 2 or a 2 then a 1. So that's 2 options. So 2/9 is my probability. And a probability of 4, I could get 2 and 2. So it does not appear that we are counting, like, if I did 2 and 2 and then I wouldn't count 2 and 2, like as 2 separate outcomes. Just, I know there was some debate on some of that in one of our other problems. So for this particular experiment, we are not counting like the doubles, like 1 and 1, or then getting a 1 and 1. Like that would be the same outcome. All right, so this is what we call a probability distribution. So again, looking at whatever x represents, so in our scenario here, it represented the sum of the 2 spins, and then what possible outcomes were, and then what's the probability. All right, what is the most likely sum when spinning a 3-section spinner twice? Well, if we look at the most, according to our chart here, the most likely sum would be 2, because it's the one with the biggest, the most outcomes and the highest probability. What is the probability that the sum of 2 spins is odd? Well, if the sum of 2 spins is odd, so that means I have 1, 2, 3. Oh, I'm sorry, I haven't got to count this correct. So this is one outcome. This is an outcome. The sum of 2 spins is odd, so there would be 4. So the outcome here is once, it happens 0 times. This is an outcome of a sum is 3. It happens twice. Okay, no, I'm looking at that wrong. All right, so this is the sum. So we're spinning a sum. The sum is odd. Sorry about that. So we have a sum that's odd, and it's happening twice. So that's 2. Here's a sum that's odd. It's happening twice. That's 2 more. So that means out of the 9 trials, there could be 4 out of the 9, because we're looking at the sum to be odd, not the outcome to be odd. Sorry about that. All right, so now let's use this, probability of success. So that was kind of like so again, this is talking about a probability distribution, just so that you understand what that's referring to. And this is going to be kind of the more elaborate version. All right, so on this one, states, according to a survey, about 62% of adults have visited a dentist in the past year. You ask 5 randomly selected adults whether they have had a dentist appointment or dentist visit in the past year. Draw a histogram of binomial distribution of your survey. So again, what we're looking at here is the binomial distribution. So in order for us to do the histogram, and I'm going to do all the work on this page, and then I'm going to show you how to do the histogram. We need to figure out the probability of success for each possible outcome. So this is where that crazy formula comes into play. So again, that crazy formula, if you go back to your formula page, gives us the NCK times P to the K times 1 minus P to the N minus K. So that's the formula that we're going to be using. All right, so on this one, let's go ahead and look at each individual, trials. So we're asking 5 people. So the number of trials we're going to use is 5. So when we start this, we're looking at the probability of having 0. Like in other words, if you ask, the probability that 0 adults went to a dentist visit in the past year, probability of 1, the probability of 2, the probability of 3, the probability of 4, I'm going to squeeze in here the probability of 5. All right, so we have 5 possible, well, actually 6 possible values that we're going to create. All right, so this is what we're going to do. Let's plug in the numbers into our formula. So N represents, in our scenario here, the number of people that we're asking. So we're selecting 5 adults. So it's 5C. K represents the trial we're on. So we're looking at what's the probability of having no adults that have visited the dentist in the past year. So that's 0. The probability of success, it says about 62% of adults have visited the dentist. So that's your success rate. So let's write that as a decimal. Raised to the K. So K is 0 in our scenario here. And then the probability of failure. So 1 minus 0.62 raised to the N minus K. So N represents 5, the number of people, minus k is 0. So 5 minus 0 would be 5. So that's what you're going to plug into your equation, into your calculator. So I'll show you how to do that. All right, so you're going to hit math. So math is right here. You're going to arrow over to where it says probability. And you're going to select this combination one, which is number 3. So what happens here is it brings up a template, right? So you're going to type in 5 and then arrow over to 0 because we want to do this 5C0. And then arrow over, and I want you to put in parentheses 0.62, and then hit the little caret key, which is this one above the division, and then raise it to the 0 power, and then arrow down, and open up another parentheses, 1 minus 0.62, because again, that's the probability of failure, raised, and then we're going to raise it to the 5th power here. So all of that can be done in kind of one step in your calculator. Let's hit enter. Let's round to 4 decimal places. So I'm going to get an answer of 0.0079. All right, and then we do the rest. So how this works is we're gonna, we still have 5. This time we're gonna use our k value of 1. So the only thing that changes here in all of these scenarios is the k value. So this is gonna be 1. And this is gonna be n minus k, so this gives me 4. So to figure out this value, I would like to see your work on your paper, so I do need you to show this. So rather than typing this in a whole bunch of times, here's what I want you to do. I want you to hit second enter, so second, and then enter. What that does is it brings up your previous answer. And so all I want you to do is use the back arrow key and change the numbers. So that way you don't have to do it again. So we're going to change this one to a 4. We're going to change this one to a 1. And we're going to change this one to a 1. So all that did is allowed us to kind of use that previous answer and then change all of our numbers. So hit enter, and now you get your new answer. So 0.0646. All right, let's do that again. So we're going to do 5C2 this time. 0.62 raised to the 2, 1 minus 0.62 raised to the 3rd power. Hit second answer, and then let's change our numbers. Okay, hit enter, and I got 0.2109. That's the probability of that happening. All right, so again, 5C3 this time, 0.62 to the 3rd power, 1 minus 0.62 to the 2nd power. I know it's tedious to have to write the work down, but, well, I'm still wanting you to. So, all right, so this is 2, this is 3, and this is 3. So I get 0.3441. Oops. All right, keep going, 2 more to go. So we have 5C4, 0.62 to the 4th, 1 minus 0.62 to the 1st. Do you notice how this is related to that binomial expansion? So I don't know if you are catching on to this, but remember when we did the Pascal's triangle, where like the first term was always raised to the highest power and the second term was always raised to the lowest power, and then for every consecutive term, every term that came next, the powers either went down or went up by 1, right? And so that's what we're doing here. This is just another version of that binomial expansion, which is why it's kind of in this section. I got 0.2808. And then the last one, 5C5, 0.62 to the 5th, 1 minus 0.62 raised to the 0. Hit second enter. Let's change our numbers here. So I got 0.0916. All right, so this is the probability of each of these outcomes happening. So the probability that nobody went to the dentist in the past year, the probability that 1, 2, 3, 4, 5 adults. Okay, so given our trial. What we want to do now is we want to create a histogram. So if you remember what a histogram looks like, and I'm going to go ahead and do this down here. So a histogram is kind of has two axes, so an x and y axes. You're going to label your axes with whatever our variables are. So our variables in this case were the number of adults who visited the dentist, so it's important to label your chart, right? Because otherwise the histogram really doesn't make any sense if you don't have the variables kind of in there. And then this is going to be our probability. So we're looking at the probability. So on the bottom here for the histogram, you have to give a range. And so what we were talking about in our scenario is the probability of, you know, no adults, 1 adult, 2 adults, 3 adults, 4 adults, 5 adults. So I'm gonna do kind of like little bars here. So a histogram basically has a range, and so because of our scenario, we're only talking about, you know, our range contains one value. I'm only going to put one number in here, but each bar, so like the bar that I'm going to draw here for this one is going to represent 0, the probability of 0 adults being, you know, going to the dentist in a year. Now the harder part is the probability on the side. So I'm going to write this, I'm going to keep this as a decimal, I'm not going to write it as percent. And so I'm going to do a count by, and again, it really doesn't matter, but let's see here. I got to go up to 0.35 approximately. So 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35. So I thought about maybe counting by 0.05 because my numbers go from pretty small, right? And then the highest number is 0.3441. All right, so that's my scale on my y-axis. Make sure you use a common scale, which means that you're, you know, the same distance between each value. All right, so then we can look at our data. So the first one is 0.0079. So 0.0079 would be probably like right here. So your first bar is going to look like this. Now you can color this in to show, like a lot of times they do that with histograms. The second one, number 1, is the probability of 1 adult going to the dentist. I got 0.06. So 0.06 would be right about here. So this is going to be my bar. Histograms always touch. So where one ends off, the other one begins. For 2, I got 0.2109. 0.21 is approximately there. And so I'm going to make this bar. Color it in a little. All right, for my 3, I got 0.344, so that's going to be the highest one, so maybe about right here. Doesn't have to be, you know, perfect or anything. For 4, I got 0.28. Which is maybe right about here. Again, obviously I'm estimating, you know, it's not 100% perfect, but it's close enough. And then 5, I got 0.09, so that's about right here. All right, that's my beautiful histogram. So a couple things if you're asking about the data here. So number 1, if you go back up to our questions, what is the most likely outcome? You don't have to do a histogram to be able to figure this out, but you probably realized that the most likely outcome was 3 adults. Also, it's our highest bar on our histogram. So we'll go back and, you know, 3 adults visiting the dentist in a year. What is the probability that more than 3 people surveyed have visited the dentist? So more than 3 people imply, not 3, more than 3, imply that we're looking at the probability of 4 and the probability of 5. because those are the only two values or data points in our survey that count as more than 3. So all I'm going to do here is take those probabilities and add them together. And I'm going to get 0.3724, which is approximately 7.24%. So again, you can change them as percent, that's easier. The other thing I want to add before we're done here, so this is what we're using our binomial distribution for, to kind of look at our success rate and kind of organize our data. How you describe data, there's 3 different ways to describe data. What we call a normal distribution, skewed left, and skewed right. So I'm going to add this to our notes. This is not in our notes, but I'm going to add it. So a normal distribution means our data is kind of normally distributed, which means that it kind of starts off high and then kind of peaks in the middle and then tails off at the end. We call this a normal distribution. If you do take a stats class, which I highly recommend, you'll do something called like standard deviations and all that kind of good stuff, and it's based off of our normal. Most of our data is kind of following this plan. So that's what we call like a normal distribution. And then we have data that can be skewed like this way, where there's a whole bunch of data on one side and then very little data on the other side. And then I'm going to draw this one over here. And then we could have kind of the exact opposite. So like, for example, I have a lot of data on the right side, but no data on the left side. So I want you just to understand what this is called. So this is called, normal distribution. You also might call it like, I don't know, like an average, or it's evenly distributed, something like that. This is called skewed. In other words, skewed means it's kind of pushed to one side. But you would think it would be skewed on the left, but it's actually the opposite. So it's skewed right. So our data is skewed the other direction. And then this one is skewed left. Again, kind of the opposite of what you would think it would be, maybe. And so anyway, this is skewed right, this is skewed left. So there's going to be a couple questions, I know, in some of the practice and so forth, that asks you about the distribution, the look of the data. And so if I was to look at my data here, and I was to describe it, I would say, kind of if I draw like a curve over, I would say it's more normally distributed than anything else, right? It all kind of peaks up in the middle, and then it tails off on the ends, so the real extremes. So again, that's kind of how we use those words to kind of describe our data. All right, that's it for now. I would practice some of this stuff. Again, a little tedious, so there's not a ton of questions on this, but at least do one, try to practice drawing the histogram, and then come to class with any questions. All right, bye for now.